All right, here we go. Well, welcome back, everyone, to week 2. So I mentioned last week that I was planning to lecture without my mask on. I want you all to know I took rapid tests this morning, and I was tested at the university tests at the end of last week. All those tests came up negative, so I have very good reason to believe I do not have COVID right now. And so I'm going to take this off, and I'm going to smile at you all. Hopefully make your day a little bit better by smiling, because I do think that I can express myself and discuss this material better when I can use my entire face. Like I said, I have really good reason to believe I do not have COVID right now, and I don't have any symptoms of any kind of sickness, so that's why I'm going to do this. All right, so energy moves when things move. That's what I've, that's how I've titled this slide. And what do I mean by that? What I mean is that we're going to be talking about a different kind of energy this week from what we did last week. We're going to be talking about a new kind of energy. So last week we talked about something called internal energies. This week we're talking about things called mechanical energies. And mechanical energies tend to do with things moving around, and so I've titled this, Energy Moves When Things Move. Energy also moves when things don't move, right? That is also the case. But today we're going to be learning about some energies that do involve moving things. But before we do that, I'm always going to start lectures by just doing a quick look at what we did last week. So, what did we do last week? We started here. Energy. So, the way we introduced energy is we said in order for interesting things to happen in the world, energy has to move from one place to another, right? That was sort of how we introduced this idea. And that is the core idea that we're going to be thinking about throughout this entire course, right? Energy moves from one place to another, and when it does, interesting things happen. And the way that we know that energy is moving is with this thing called an indicator. So we can't measure energies directly in the lab, but we can measure other things that tell us about what those energies are doing. So last week we looked at thermal energy and bond energy, and the indicator of thermal energy is temperature. And we know that thermal energy is changing when temperature is changing, right? We can't measure thermal energy, we can measure temperature. And if we see that temperature is changing, that immediately tells us that thermal energy is changing. The other one was bond energy. And how do we know that bond energy is changing? We know bond energy is changing when the phase of a substance is changing. So when it goes from a solid to liquid, when it goes from a liquid to a gas, or the other way, right, gas to liquid or liquid to solid, that is how we know that these energies are changing, right? And what I said was, and we'll talk about our first quiz, which is next week, sort of at the end here, but what I said was often what's going to happen in a physics problem is I'm not actually going to give you the amount of energy that we have. What I am going to give you is indicators. And you're going to have to use what you know about indicators to determine which energies are changing. And then we introduced what I'm calling the big idea of Physics 7a, because everything that we do from here on out is going to involve this. Everything that we're going to do from here on out is going to involve this. And it says that energy never appears from nowhere or disappears into nothing. Energy never appears from nowhere or disappears into nothing. It is always moving from one place to another. And so a big part of our job over the next 10 weeks is going to be to figure out what energies exist and where they're going. That's going to be the basic problem that we're trying to solve throughout this class. We have some kind of energy, it's moving to somewhere else, and we want to keep track of that, right? And we introduced these two equations to represent that. So if you watched my, again, I didn't ask you to do this, but it's available to you if you want it. If you watched my short lecture video on this topic, the example I gave involved I had 2 glasses of water. And I imagined 2 cases, one case in which I'm just pouring water from one glass to another. And if that's the case, that is a system where, that is the case where the system is closed, right? That is a case where the total amount of energy inside of your system is not changing. Now the energy is going from one kind to another, right? The amount of water in each glass is changing as I pour the water from one to another. But if I add up all the water in the 2 glasses, that number is not going to change. But what happens if I pour some of the water out, or if I go to the tap and I put some more water in? Then that total amount of energy inside our system, the total amount of water inside our glasses combined, is allowed to change. And in that case, we introduced this idea of heat and work. And all that we know about heat and work up to this point is that they're just ways that energy can go into or out of our system. Right? They're just ways that energy can go into or out of our system. For heat, that's pretty much all that it is. Right? Typically, heat involves one object which is warm, one object which is cold, and then energy goes in between them. Right? So an example of a case where we might think about heat is you take a pot of water and you put it on the stove. Right? The stove is going to warm up the water. How is it going to do that? We would say it does it by transferring heat into the water. The work piece, we're not going to worry about too much yet. Work, we'll say for next week. You'll see a little bit of it in DL, and then we'll do the rest of it next week. Okay? So let's not worry too much about work yet. I don't know why that question is there, to be honest. I don't think that's what's on my next slide. But I want to take a little aside here to talk about units. So we didn't really talk about units last time. So this is, I'm kind of breaking up the review with this thing about units here. And I just want to talk about these for a minute so that we're all on the same page. So first off, mass is measured in kilograms. Let's be clear about what mass is. Mass is just a measurement of how much of something you have. Right? So you might say, this is an object that weighs 30 kilograms. That's a little bit of a misnomer because kilograms is not a weight, it's a mass. There's actually a difference. But sometimes I'll say this weighs 30 kilograms. Sometimes you'll say it is a mass of 30 kilograms, whatever, right? It's just, this is how we measure the amount of stuff that we have until we get to moles. But we'll save that for then. Energy, and I might not have said this explicitly, but energy is measured in joules. It's called a joule because there was some guy in the 19th century named Joule who was interested in energy. That's it, right? It's called a joule. It's denoted with a capital J. Now, one thing I want to notice here is that the prefix kilo just means 1,000. If you've taken a lot of science classes already, you perhaps know this. If you haven't taken as many science classes, you might not. But the prefix kilo just means 1,000. So what is a kilogram, or a kilogram as we would usually pronounce it? It's 1,000 grams. What is a kilojoule? It's 1,000 joules. So you might be given a problem where something is measured in kilojoules. It's not a new unit, right? It's not a new unit. It's the same unit as before. It's just that now we have 1,000 of them. That's all. For now, we'll measure temperature in degrees Celsius. Degrees Celsius. We will use Kelvin later in this course, but for now it's just degrees Celsius. And distances are measured in meters. Meters about, I don't know, a little over 2 feet, something like that. Distances are measured in meters. Time, in case you care, is measured in seconds. We measure time in seconds. It's not on this list. But these are the units that we're going to be using for now. For now. We'll introduce a couple little ones in the future, but all of these will show up throughout the course. Now, why am I spending time talking about units? The reason I'm spending time talking about units is because units actually give us interesting information. Units actually give us interesting information. So let's look at an example. So this is the specific heat of water. You don't need to write this down or memorize this, right? Because I would give it to you on a quiz if you needed it. But if you've taken some chemistry classes, this is a number you're probably very familiar with, right? The specific heat of water is 4.184. Liquid water, that is, not solid or gas. Liquid water. It is 4.184, but 4.184 what? Kilojoules per kilogram degrees Celsius. What does that mean? What does kilojoules divided by a kilogram degrees Celsius mean? Well, we can think about that by looking at this equation and recognize that to get an energy, we have to multiply this number by a mass and multiply by temperature. If we multiply this by a mass and temperature, we'll end up with just kilojoules. So what does this unit mean? By saying kilojoules per kilogram degrees Celsius, what it means is that if we had 1 kilogram of water and we wanted to increase its temperature by 1 degree, we would need 4.184 kilojoules. That's what the units mean. If we had 1 kilogram of water and we wanted to increase its temperature by 1 degree, then it would require 4.184 kilojoules per kilogram, or kilojoules, right? If we had 2 kilograms, it would take twice as much. If we had half a kilogram, it would take half as much. A 4.184 joules is actually another interesting number. Does anyone, there's another thing that we call 4.184 joules. Does anyone know? Yeah. Yeah, it's a calorie. it turns out that if you use calories in some chemistry classes, it's this. 1 calorie is actually the amount of energy it requires to increase 1 gram of water by 1 degree Celsius. But if you look on the back of if I'm remembering correctly, like on nutrition facts, the things that we call calories there are actually kilocalories, if I'm not mistaken, right? So this number is 4.184 kilocalories or 4.184 calories, like you would see on a package of food or something. Okay? Not necessary information, just fun fact. Okay. So whenever you're solving problems in physics, it is worth your time to pay attention to the units. Again, for a couple reasons. Number one, the units give interesting information. And the second thing is if you're going through your problem and you come to a part of the problem and you're looking at your units and your units do not make sense, that is a good sign that that you've made some sort of mistake somewhere. That is a really good sign. What you do not want to do is look at what you have and say, well, the units don't make sense here. Let's just keep going and hope they work themselves out. That is not a good plan, right? Your units should always make sense in the context of your problem, and if you don't, there's an issue. And you have to take a look to see what that issue might be. But also, right, you can check your answers at the end and say, does this unit make sense? So for example, if I asked you to calculate a final temperature, and you do all your math and you come to an answer that's in joules, that is a sign that there's a problem, right? Because we do not measure temperature in joules, we measure temperature in Celsius, degrees Celsius. And so it's always worthwhile to look at your problem, look at your units and make sure they all make sense, and go from there. Okay. This is back to that review. I don't really need this slide, right? We're going to do a practice problem that's sort of similar to this later. But these are the two energies that we worked with. And these are the kinds of problems that we might see. Like I said, I'm going to actually do a practice problem at the end of lecture today, so we'll just wait for that. Okay. The other thing that we saw, I didn't actually talk about it in lecture this week, but this was in the video that I asked you to watch, and you talked about it in DL, is this idea of an energy interaction diagram. So an energy interaction diagram, right, is a way of organizing information about your problem. And in some senses, it's a part of the solution. Now, you never, if you do not want to, you never have to draw an energy interaction diagram. It's not required, but it is a good way to organize information, and it is a good way for me or for the grader to look at your work and understand a little bit more about what you were thinking. And if we understand a little bit better what you're thinking, it is then easier for us to give you partial credit. So if you've taken physics before, and you're really, really comfortable with it, and you're just like, yeah, I see this problem, I can write down an equation right away, it's correct, and solve it, done. That's fine, right? You'll get full points if you do it correctly. But if you're not comfortable doing it that way, which I suspect is true for most of you, this is a tool that you could potentially use to help make that process a little bit easier, right? Can I do that? Can I look at a problem and write down an equation? Yeah, but I've been studying physics for like 10 years at this point. Right? It's not expected that you should be able to do that. But if you can, that's fine. Right? But one of the really nice things about the energy interaction diagram is, first off, you're representing the information. But if you draw a correct energy interaction diagram, it is then always possible to write an equation. And the way that you do that is you just write one change in energy for each bubble. Right? So this energy interaction diagram has 3 bubbles, 1 bond energy bubble, 1 thermal energy bubble for the water, and 1 thermal energy bubble for the coffee, and you get, boom, bond energy change, thermal energy change, like that. Done. And because it's a closed system, that whole thing is equal to 0. Right? So again, this is a great way to get partial credit. Because again, you're sort of showing me, you're showing the grader your knowledge of the physics that's going on in the problem. And that is really what we care about. I do not care if you can do algebra at the end of this class. I just don't. We have to do algebra, but I don't really care so much about it, right? What I care about is that you can show me that you have a sense of what's going on in the physics, and that's what this does. Okay. So we are now going to move on to a new kind of energy. I say new kind of energy I don't really like that framing because it's not really any, there's nothing new about this, right? We call them mechanical energies. They are it's just a different category of energy. But I want to start by talking about the ways they're exactly the same to the energies that we've already seen. And that's these. Mechanical energies are no different from internal energy as far as energy conservation and interaction is concerned, right? So everything we know about energy still applies here. So mechanical energies don't just appear from nowhere and disappear into nothing. That's just a fact about energies, right? Mechanical energies have an indicator. That's just a fact about energies. Mechanical energies can change into other kinds of energy, right? That's just a fact about energy. In that way, they're exactly the same as any other kind of energy. You can still draw an energy interaction diagram. There's still an indicator, all this stuff. So what makes mechanical energies different? And what makes mechanical energies different is that they depend on things like the position and speed. And to put it more specifically, what we mean by that is that in order to determine the mechanical energy of an object, you have to compare it to something else. You have to compare it to something else. So think about thermal energy for a second. That's an internal energy. We do not have to compare our object to anything else in order to understand the thermal energy of our object. We need to know its temperature. If we know its temperature, we're good to go. That is not true with mechanical energies. And you maybe have never thought about this kind of thing in this way, but let's imagine that I have this object and I throw it across the room. I'm giving it mechanical energy, right? What kind of mechanical energy? We'll talk about that in a minute, but I'm giving it mechanical energy. But it turns out in order for me to recognize that this object has mechanical energy, I have to see that it's actually moving with respect to, say, the ground, right? Or if I'm moving across the floor, I have mechanical energy because I'm walking, but I would not be able to know that I have mechanical energy without having something here to compare to. If I was out in space and there was nothing around me, I would have no way of knowing that I was moving because I would have nothing to compare myself to. Right? You have to have something to compare yourself to in order to see that you have mechanical energy. Right? That's what makes mechanical energies different from internal energies. But again, in every other way, they're exactly the same. In every other way, they're exactly the same. So let's look at them. We'll just look at them at a high level, and then we will talk about each of these individually. Yeah?
Do you mean that we have to, when we need to measure it, we need something to compare?
Mm-hmm.
Or do you mean that the energy of it depends on the other stuff, not depend on itself?
It's a good question. I'm trying to think how to answer it. It's a really good question. So the answer is the energy typically always depends on it and then something else in the system. We'll see examples of that in a second. Right? In some cases, you're not really going to have to think a lot about this a lot of the time, but there are certain cases where you might have to. And I'll talk about which is which when we talk about each of these energies individually. So we'll get there. Thank you for asking. Okay, kinetic energy. So why do I want to start with kinetic energy? Because it's the one that probably makes the most sense. If I throw this across the room, it's moving. It has energy because it's moving, right? This hopefully is, if we think about what energy is, it hopefully makes some amount of sense that an object that is moving has some kind of energy. That energy is called kinetic energy. Okay, that's probably the most obvious one. Okay, this one is much less obvious, perhaps, but it's a thing called gravitational potential energy. Gravitational potential energy is energy that an object has because it is above the ground. So now I'm holding it up here. It has this thing called gravitational potential energy. We'll talk about what potential energies are here in a minute, but it has this thing called gravitational potential energy, and if I were to drop it, it would fall. And one of the ways to think about why it would fall is that it has gravitational potential energy, and when I let it go, that gravitational potential energy is being converted into kinetic energy. Right? That is one way to think about why this object falls. Again, we're going to talk about each of these in depth. And then this third one is called spring potential energy. So you might be asking, why a spring? A spring, it's like a little coil, right, that can stretch and compress and all this stuff. Why are we talking about springs as opposed to all the other things we could think about in the world? We'll talk about that when we get to the springs. Okay? But these are the three main types of mechanical energy that we're going to be working with in this course. There's one more, sort of, that we're going to learn about in a week or two. But we'll get there when we get there. So let's start with gravitational potential energy. let's start by asking ourselves, what is a potential energy? Now, if you go online and you search for a potential energy, you'll probably see a definition like a potential energy is an energy that an object can potentially have, which is not very helpful, right? It doesn't really mean a lot. It just takes the words and rearranges them. And I also don't like that because it's still energy, right? Because that sort of phrasing of it implies that potential energy is energy that an object doesn't have but could have in the future. For our purposes, that's not the case. Potential energy is a real energy. It's just as real as any other kind of energy. But what makes it special? What makes it special is this, is that if left to its own devices, an object is always going to convert its potential energy into a different kind of energy, usually kinetic energy. So for example, this object has gravitational potential energy. If I let it go, it converts that gravitational potential energy into kinetic energy, right? That's always going to happen when you have potential energy. Given the option, you're always going to be converting your potential energy into some kind of energy, which again is usually going to be kinetic energy. Not necessarily always, but usually kinetic energy. And so the example is a falling object, right? Because, again, while I'm holding it here, I'm preventing it from doing what it wants to do. But as soon as I give it the option, it converts that potential energy into kinetic energy until it hits the ground. So gravitational potential energy. Gravitational potential energy is something that an object has because there's something else pulling on it. Because there's something else pulling on it through gravity. In our case, what is the thing that is pulling on us usually? It's the planet Earth, right? It's the planet. Everything pulls on everything else, right? You're actually pulling back on planet Earth just as hard as Earth is pulling on you, which is kind of wild to think about, but it's true. The difference is the Earth is huge, right? And we're much smaller. But the point is, whenever you have one object and a second object and they're pulling on each other through gravity, you will have this thing called gravitational potential energy. Now, there's a lot of different ways of talking about gravitational potential energy. But for our purposes, this is the equation that we're going to use. Gravitational potential energy is equal to the mass of an object times this gravitational acceleration g, which I'll talk about in a second, times the height of the object. So let's say I'm holding this object right here. It's like, I don't know, 2 meters above the ground or something. I don't know, however high it is. That would be the height here. The mass is what we talked about. And then g is this thing called the gravitational acceleration. Why is it called an acceleration? Let's save that for Physics 7b. If you take Physics 7b, you will learn why it's called the gravitational acceleration. But for our purposes, it's just a number that we plug into the equation. And again, also for our purposes, when we're talking about, most cases we're talking about, we'll be talking about gravity on Earth's surface. And when we're talking about gravity on Earth's surface, g is going to be equal to 10. G is going to be equal to 10 meters per second squared. Again, it's just a number that goes into the equation, yeah.
Based on the definition of things pulling towards each other,
Yeah.
do magnets have gravitational?
Oh, good, yeah. So magnets do have gravitational potential energy because they have mass and they're pulling on each other through gravity. But what we think of as being the magnet is a different effect. We're not going to study magnets in this course. They're super cool, but we're not going to study them in this course. You will study magnets in Physics 7c if you take Physics 7c. So good thought, good question, but that is a different effect, yeah. And when we're on the surface of the Earth, so is it true that like I'm pulling on you, I'm pulling on all of you a little bit because of gravity? Yeah, but by far the overwhelming majority of gravity is coming from the Earth right now. And so for our purposes, we pretty much just assume that all of the gravity that we care about is coming from planet Earth. Now, what's one little twist I could put on a problem? What's a twist I could put on a problem here? I could say, let's do this on the moon instead of the Earth. Let's do this on the moon instead of the Earth. How would we handle this? What I would do is g would not be equal to 10 anymore. It'd be smaller. I believe g on the moon is like 1.6 or something like that. I don't know the exact number, but it's like 1.6, 1.7, if I'm doing my math right. So all that means is you would just plug a different number into the equation. But everything else would be the same. All the other stuff about gravity would be the same. It's just that we would have a different number to plug in here. The thing that will be changing during your problem, the indicator that tells you that gravitational potential energy is changing, is the height. So somebody asked me, in the last lecture. They said, so what if you like have a ball sitting at the top of the hill, but it's like on the ground on the top of the hill, right? Then it's on the ground, right? And the answer is that height is kind of a little, we're going to spend time talking about what exactly height means in certain contexts. It turns out it's a little bit fuzzy what it means. But the point is, if your object is above somewhere else, it has gravitational potential energy. So if you put a ball at the top of the hill and you give it a little push, it's going to roll down to the bottom of the hill, right? Because even though it's not like falling per se, it's still going down, right? That's the idea behind gravitational potential energy. Okay, so the next one, and again, this is the one that's hopefully a little bit more intuitive in the sense that it makes sense that an object that's moving around has some amount of energy, is this thing called kinetic energy. And it's very simple. An object that is moving has kinetic energy. An object that is not moving does not have kinetic energy. That's it. How do we calculate kinetic energy? Well, kinetic energy depends on two things. It depends on the mass. It depends on how heavy the object is. So for example, if I threw this at the door and then threw a bowling ball at the door at the same speed, it makes sense the bowling ball is going to do a lot more damage to the door. Why? The bowling ball has more energy because it has more mass. It has more, even if it's traveling at the same speed, the bowling ball has more kinetic energy because it has more mass. Okay, what about the speed part? First off, why is speed represented with v? That is a great question, and the reason is that technically what we're talking about here is not speed, it's velocity. Now, we're not going to spend time in this course thinking about the difference. There will be a little bit of that in Physics 7b, when and if you take Physics 7b, but we're not going to be talking about the difference in this course. But we're going to leave it as a v, because that's the letter that's used in physics. But all that we mean is just the speed that the object is traveling, how fast it's going. We measure that. There's a lot of different ways to measure speed. We measure that in meters per second. So an object that's moving at 1 meter per second would just move 1 meter every second. Although we should notice that it's not actually the speed that goes into the equation, but the speed squared. The speed squared. Right? So for kinetic energy, the indicator is speed now. Right? If the speed of an object is changing, then its kinetic energy will also be changing. Okay, so now we get to the springs. So the first question is, why springs? Why are we spending our time on springs? And the reason is that there's a lot of things, it turns out there's a lot of things in nature, and one thing in particular, which we're going to study in a couple of weeks, that can be thought of as being sort of a spring. Right? It's sort of a spring. It's not exactly a spring, but it's sort of a spring. Right? So a spring is this, right? It's a little coil. There's going to be some springs in the DL classroom over the next couple of weeks you're going to get to play with and get a sense for how they work. But a spring is just this little coil that can stretch and compress. That's all, as far as we're concerned. And so how do we know when a spring has potential energy? Well, we have to introduce this idea of an equilibrium length. So this spring is just sitting on a table. It's not doing anything interesting. There's nothing pulling on it. There's nothing pushing on it. And when that's the case, the spring is going to be a particular length. And that length is what we call the equilibrium length. It is the length that the spring wants to be naturally. When a spring is sitting at its equilibrium length, at its natural length, it just doesn't have potential. It doesn't have any potential energy. This spring does not have potential energy because it's just sitting at its natural equilibrium length. But if we take that spring and then pull it, stretch it out, or compress it, push it in, then it's going to store potential energy. And if we let it go, it's going to bounce back to where it was before. Right? So how do we represent that? We represent that, the indicator of spring potential energy is this thing called the distance from equilibrium. So let's say you had a spring that if you just set it on the ground and didn't do anything to it was 1 meter long. And then you took that spring and you stretched it out until it was 1.3 meters long. Okay? We would have stored potential energy in the spring, and the distance from equilibrium would be 0.3 meters. The spring wants to be 1 meter long. You've stretched it out to 1.3 meters, so its distance from equilibrium is 0.3 meters. But let's do the opposite thing. Let's take the spring now and compress it. So now you have that same spring that when it's doing its thing just wants to be 1 meter long, and you take it and you push it in so that it is now 0.7 meters long. We have again stored spring potential energy, and in this case our distance from equilibrium is negative 0.3. But there's a funny thing about springs, which is that they do not care whether you've stretched or compressed them. Notice, in this equation, the distance is squared. And so if you take a spring and stretch it out, so it's 0.3 meters longer, it's going to store the exact same amount of potential energy as if you took it and compressed it in so it was 0.3 meters shorter. And so while it's true that our distance in that case is technically 0.3, it doesn't really matter because you're going to square it anyway. Right? So you look at how long the spring wants to be naturally. You look at how long it actually is. You look at the difference, you plug that in, and you get the spring potential energy. This K value is what's called the spring constant. You can just think of it as being how stiff the spring is. The higher the spring constant, the stiffer the spring. Okay? You'll get the chance to work with springs a lot more over the next few days, next week or so. So that's a spring. Like I said, why are we introducing springs? Well, because there's just a lot of things in the world that turn out to be very similar to springs. And we use them all over the place. Okay. So, as far as new content is concerned, like I said, I'm going to spend some time working on a practice problem here in a minute. But as far as new content is concerned, that's what we have. Okay? There is one topic. I am going to let you out early today, not 50 minutes early like we are now, but I am going to let you out early. There is one more topic that I want you to look at. Just like last week, I'm going to let you out early, but give you a little video to watch. So if you go back to our Canvas page, what is at the top there now, instead of sort of the beginning of quarter stuff, is the week 1 and week 2 content. And if one of the pages that's linked there is the week 2 short lecture videos. These are the lecture videos that I made 8 months ago or whenever it was. And just like last week, if you click on the week 2 lecture videos, the video right at the top, it's going to say, just try to watch this before you DL. So it's just a topic that I'm not going to cover in lecture, but you are going to see in DL a little bit. So there's a lecture video there if you need a little bit more work with it. Yeah, so that'll be there. But as far as the new content is concerned, that's all I have. So I'm going to talk about the quiz for a second, in a second. And I'm going to do a practice problem, but I'd like to take a little aside for something that you all do not need to know, that you don't need to take notes on. But I'd like to talk about it because I think it's fun. And it's this. So we've been talking about conservation of energy. We've been talking about conservation of energy. And I've said last week, I don't know if I said this explicitly or not, but I do think I said it at some point, is there are no truly closed systems in the world, right? There are no truly closed systems. There are some things that we can think about as being basically closed, but there are no truly closed systems. And this might lead us to an interesting question, which is energy conserved on the scale of the entire universe? There's a lot packed into this question because this is a really complicated idea. What do I even mean when I say the entire universe, right? This is how we're going to define the entire universe. What I'm going to say is, let's imagine you just zoom out, and you zoom out some more, and you zoom out, and you zoom out, and you zoom out, and you keep zooming out until it's literally impossible to zoom out anymore. What you would be looking at is what I would call the entire universe. It's everything that we know of, everything that we can see, and a lot of things that we can't see. Now, you might say to yourself, well, of course this is a closed system, right? If anything is a closed system, then it would be the universe. And you'd be wrong. It turns out the universe does not appear to be a closed system, which is really weird. It appears to be either that there's something inside or outside of the universe that is putting energy into it, or the universe is able to just make energy on its own somehow. Remember when I said that energy can never appear out of nothing? I lied a little bit. At least we don't have a good explanation for why it happens here. For our purposes, it's true. But it turns out for the entire universe, it's not quite true. And how do we know this? Right? So this is a really big thing to say. Right? The universe is not... there's more energy in the universe now than there was yesterday. That's kind of weird. How do we know this? Well, you look at this picture. We look at this picture. This picture was taken by the Hubble Space Telescope. And you might look at this and you say, wow, there are a bunch of stars. That's nice. But you wouldn't be quite right, because it's not stars. If we zoom in a little bit, what we see is that we're not actually looking at stars. We're looking at galaxies. So this galaxy looks sort of like the Milky Way a little bit. It's not the Milky Way, because we're inside the Milky Way and we can't take a picture of it. But it sort of looks like the Milky Way. It's actually collections of hundreds of billions of stars. And until the early 20th century, it was not actually known that there were other galaxies besides our own. You all know Betty White recently passed away? Very sad. She was born before we knew there were other galaxies. That is wild. She was born before we knew there were other galaxies. So there was this guy working at this observatory called Mount Wilson, which is in Pasadena. This was 100 years ago, so you could actually see the stars. But anyway, he was working, and he looked out and he saw all these galaxies, and he discovered something very interesting about them, which is that if you look at the galaxies, almost all of the galaxies in the universe are flying away from us as fast as they possibly can, which is weird. Now, I can think of a couple reasons why everything in the universe might be trying to get away from us, but those are not very scientific reasons. And so the question is, why is this? You have to come up with some sort of scientific explanation. And the explanation that he came up with, and the explanation that we use to this day, is that the universe is expanding and getting bigger. Now, that on its own does not mean that the universe is just gaining energy. But in the 90s, we discovered something else. It's not just that the universe is getting bigger. Is that every day it's getting bigger faster and faster and faster and faster. It's like you took this, you threw it up in the air, and instead of turning around and coming back down, it just kept going up faster and faster. It doesn't make a lot of sense. We have some explanation for why this is the case. It's not a very satisfying one, if you're asking my opinion. The basic explanation is just that this is how the universe is. And we've tried all these other things to explain it, and they all come out totally wrong. And so, this is one of the big open questions in physics. The universe is not a closed system. It appears that energy is coming into it. Where it's coming from is not totally clear. Yeah?
What does it expand into?
Good question. So this question comes up all the time. When I say the universe expands, the question that gets asked, and it's a really good question, is what is it expanding into? And the reality is that the universe does not behave the way that we think it is. So the way that we're probably thinking about this in our head is that the universe is like a balloon, and it's getting blown up and getting bigger. It turns out that's not the case. It turns out because of the way that space and time work, you don't have to expand into anything. You can just expand. You just get bigger. The universe just creates more space. Then that's it. It's weird. It's weird. Yeah, she doesn't like that. And it's fair enough, right? That is a weird thing, right? And it does not make a lot of sense. And that's fine, yeah.
Have we actually been able to discover like other universes, or is that just?
Good question. Are there other universes? Is the question. Have we been able to discover them? There are hypotheses and theories that suggest the existence of other ones, but we have no confirmation of those. There are people in the physics building who work on that stuff. That's not my particular area of expertise, but there are people who think about that. Yeah, good question. Like I said, it's weird. Yeah.
Are there theories of how we're getting energy outside of the universe and it's coming in, or do we just not know?
There are theories. So the leading theory on this point is that empty space just has some amount of energy in it. So if you took space and you took everything out, it's a perfect vacuum. There's nothing in it at all. It would still have some energy. And so the universe expands. It creates more space. That space has energy. And so the amount of energy in the universe is going up. That's the current best idea. But the problem is we don't have an explanation for why this happens. We don't have an explanation for why space just has energy or for why it has the amount that it does. That's the part that's weird. Yeah.
As a physicist,
Uh-huh.
how many times a week do you have like existential crises?
A lot, especially at the beginning. As I get a little, more than once a week. Yeah, it's a good, we have existential crises that just happen. But then you sort of just spend a lot of time working with it and you kind of get used to it. You're like, well, everything is, I can't understand any of it and that's just the way it goes. We try to understand it, that's our job, but it depends on the day. All right? Okay, so I just wanted to talk about that again, not because you need to know it, but because I think it's really cool and it's exciting and it has to do with energy, something that we've been discovering or something that we've been discussing. Okay, so now we're going to switch gears and talk about the first quiz. So the first quiz is next week. Right after we're done here, I will post practice quizzes on Canvas. I'll send out an announcement and everything, so look for that. I think there are, I believe there are 7 of them that I have, so there's a good sort of set of practice quizzes for you to work on. I will post solutions to all those practice quizzes on Thursday. So I'm just going to post the quizzes now to give you a chance to work with them without the solutions, but I will post the solutions on Thursday, which should give you enough time to look at them, right? The details are fairly straightforward. When is it? It's April 11th, yeah.
Can you bring a graphing calculator?
Yeah, that's fine. Yeah, I don't care what kind of calculator you bring. So it's next week, Monday. It's going to cover these topics: energy interaction, thermal energy, and heat. You're not going to have to worry about mechanical energy. So we talked about mechanical energies today in class. You will see them on a quiz or your final at some point. I'm not going to put them on next week's quiz. But you do need to know about energy interaction, thermal energy, bond energy, heat. Where is it going to be? It's going to be here. It's going to be at the beginning of class. So right at 9, the first thing you're going to do is you're going to walk in, you're going to take the quiz on paper. So I will give it to you. Yeah, you don't need to bring anything to write on. Yeah. It depends on what it depends on the particular setup that I come up with. Usually what it is it's, you have, again, we're going to look at a practice quiz here in a second, but usually what it comes out to is it's one sort of scenario with with like 2 to 3 sub-questions. That's usually what it comes in. It's not going to be like 2 questions in the sense that I'm going to tell you about, I don't know, I'm going to be like, it's not going to be, I'm going to be like, hey, here we have water on the stove, answer a question about water on the stove, and let's switch to like icebergs floating in the Arctic and talk about it. That's not what I'm going to do. I'm going to give you one scenario and then ask you a couple questions about it. Yeah.
So is it made to be like a lighter quiz? Like, are we going to have lecture after or just the quiz?
No, we will have lecture after, yeah. Yeah.
How much time do we have to do?
It's usually 20 or 25 minutes. I haven't decided. It's going to depend on the question I write, whether it'll be 20 or 25 minutes. Yeah. If you forget your regular calculator, I will allow you to use a calculator on your phone, but I would strongly, strongly prefer you bring your own calculator. I have a few extras that you can use if you want, but please bring your own calculator if you have one. I would, yeah. So yes, bring a pencil and a calculator. If you're feeling really ambitious, you can use a pen. I would not. I would strongly recommend using if you are super confident in your physics skills, then you can use a pen, right? I would strongly recommend that you use a pencil. Okay, I would recommend using a pencil. Now I want to make a comment about the calculator thing again, is that yes, I want you to bring a calculator because I am going to give you numbers. I am going to ask you to calculate something, but remember what I said last week, which is that if you're solving a quiz problem and you do, and you did get all of the physics right and you draw a nice energy interaction diagram and you've got all your indicators and you do that, and then you write down an equation that's right, and then you do a little bit of algebra to get the final answer and you make a mistake in the algebra and you get the question wrong, get the final answer wrong, you're still going to get the overwhelming majority of the points, like 90% and up. So while you do need a calculator to get the final answer, it's really just that. It's really just getting the final numerical answer. What I'm really interested in checking is, can you take this scenario and can you build a model for it and explain the physics that's going on? And then if you can do that well, then you can do some algebra and get the answer out, right? So just keep in mind that's what the calculator is for. It's not for solving the problem. It's for giving you a final numerical answer at the end. And like somebody asked, can you use a graphic calculator? Yeah, it does not matter to me what kind of calculator you use, as long as you give me enough information to show that you've solved the problem. If you just were to write out, if you just did everything on your calculator and then wrote the answer down and didn't give me anything else, that is 0 points. You have to show me that you know what's going on. You can't just solve it on the calculator, right? So, yeah. Okay? So, let's do a practice problem. Okay? So this problem I'm going to show you is one of the practice problems that will be posted later today. It is a problem that I wrote fall of 2021, so 2 quarters ago. And one thing that I really strongly encourage is, I'm not going to do it here, but when you first get a problem, it is really valuable to read the problem multiple times. Why is that? Why do I recommend reading the problem multiple times? Well, the reason is that typically these problems are going to have a lot of information in them, and it's not always going to be totally obvious when you first see them what information is important and where to find that information. Right? And so if you read the problem multiple times, it doesn't take too long, presumably, but it does allow your brain to take a second chance at finding the information that's important in the problem. So let's read it together. I'm going to read it out loud. So casting iron involves heating solid iron until it is a liquid and then pouring it into a mold. The iron is allowed to cool and re-solidify in the desired shape. In general, this involves adding additional materials, but we will focus only on the iron for this process. Okay, here's the first question. A 0.75 kilogram lump of iron, initially at a temperature of 20 degrees Celsius, is placed in a furnace. The furnace heats the iron to 1,650 degrees Celsius. Determine the amount of heat that is added to the iron during this process. You may find it useful to draw an energy interaction diagram, but are not required to do so. Some useful constants and equations can be found on the back of this page. So remember I said you do not need to memorize any equations. You don't need to memorize any constants for this course. If we scroll down here, we can see that everything that we might need, all the equations, all of the numbers are here already. Okay? So, again, the first thing I recommend that you do when you see a problem like this is read it again. I'm not going to do that here. I'm going to give you the opportunity to read it. You can read it yourself once I post it, all that good stuff. But the first thing that we always want to do in Physics 7 when we're trying to answer a question is start asking questions that might lead us to interesting pieces of information. And one of the most valuable questions that we can ask in this course when solving a problem for the first time is, what kind of energies are in my system? Are they changing? Almost every single thing that we will study at any point in this course is going to involve energy. And so this is a really good question to ask. Even when we get to the end of class and we're looking at systems that are totally different from this one, it will still be worthwhile to ask the question, what kinds of energy are in my system and are they changing? Let's start with one that is maybe a little bit, this is the most obvious one in my opinion in the problem. It is the thermal energy of the iron. So notice the iron is initially at a temperature of 20 degrees Celsius, and then the furnace heats the iron to 1,650 degrees Celsius, right? So that is very clear. The temperature of the iron is changing, and temperature is the indicator of thermal energy, right? So because temperature is changing, we know that thermal energy is changing. So we have one kind of energy, thermal energy. But I'm going to claim there's a second type of energy that is changing, and that the problem has told us that this energy is changing, but not quite as obviously. And that is the bond energy of the iron. So let's look at the first part of the problem again. So even though it's just the setup to the problem, it may contain interesting information. So it says, casting iron involves heating solid iron until it is a liquid. So it does not tell us, part A of this problem does not tell us for sure that the iron is turning into a liquid, but the setup to the problem strongly implies that that's the whole point. That the whole point of this process is to turn it into a liquid so that we can cast it. But there's more information besides that guarantees to us that the iron is melted. Notice what the final temperature of the iron is. It is 1,650 degrees Celsius. And if we scroll down here, we'll discover that the melting temperature of iron is given in our constants. The final temperature of the iron is greater than its melting temperature, and that guarantees to us that the iron is turned into a liquid. So again, this is going to happen sometimes. The problem does not say explicitly this iron, it doesn't say the furnace heats the iron up to 1,650 degrees Celsius and melts it. It doesn't say that, but the information telling you that the iron has been melted is there. It is there. You just have to be a little bit careful with your reading. And this is one of the reasons why I strongly encourage you to read a question multiple times. Because that information, you might have missed it on the first time, which is totally normal, right? When you're reading questions, reading problems for the first time, it is pretty much impossible to pick up all the details on a single read-through. And so that's why I can encourage you, read the problem twice. The information is there, I promise you. It just might not be totally obvious on the first time, but it is there. So now let's start thinking about, so we've asked our first question. Our first question was, what kinds of energy are in our system, and are they changing? So we know thermal energy is changing because temperature is changing. We have just discovered that bond energy is changing because the phase changes. And so now we can start drawing an energy interaction diagram, right? And this is what we usually want to do. Again, do you have to draw an energy interaction diagram? No, you do not. You are not required to draw an energy interaction diagram, but I really, really encourage you, especially if you're doing physics for the first time here. If you're doing these kinds of problems for the first time, I really strongly encourage you to draw an energy interaction diagram. Because if you draw an energy interaction diagram, it helps me or it helps the grader look at your quiz and understand what your thought process is. And the more we understand about your thought process, the more partial credit we can give you. The more we understand about your thought process, the more partial credit we can give you. Yeah?
For this question, did you say that it goes from solid to liquid to solid, or just solid to liquid?
Just solids liquid. Yeah, just solids liquid. So we're starting with iron at 20 degrees Celsius. Iron at 20 degrees Celsius is solid. We're going to iron at 1,650 degrees Celsius. Iron at 1,650 degrees Celsius is a liquid. And we're not doing anything else after that. Good question. Yeah?
Just based on common sense, because with drawing our energy interaction
Yeah.
diagram, we want to do open or closed.
Mm-hmm.
This is an open system since it hasn't been stated that it's like insulated or.
That's right. So there's another reason that you can actually figure out that it's an open system, and I'll point that out in a minute when we get there.
Okay.
But yeah, it's a good question. So these are the kinds of questions you can be sort of like spinning around in your head as you're solving problems. Yeah?
So, like, are we going to be given the melting points for things, or
If you need it, yeah.
how are you able to determine that if you feel liquid?
Because it is right here. So for the iron, the melting temperature is 1,540, and we end at a higher temperature than that. So if your temperature is above your melting point, then you have to be a liquid, or I guess you could be a gas, but I don't know how hot you have to get iron to turn it into a gas, but my guess it's pretty warm. So we're not there. So yes, we're above the melting point, so we know this is a liquid. Okay, so the next thing we might try doing is drawing an energy interaction diagram. And the way that I like to draw my energy interaction diagrams, and you don't necessarily have to do it this way, but I think it's an interesting way of doing it, is to do it in chronological order. So just think about your system and think about what's going to happen and start with the first thing that's going to happen and then go on and just, I'm not saying this very well, but the point is, like, it's going to take time for this to happen. What's the first thing that's going to happen? What's the first thing the iron is going to do when it gets into the furnace? It's going to start warming up, right? The first thing the iron will do is it's going to warm up to its melting temperature, right? We know the iron is going to melt, but before it melts, it has to warm up to the melting temperature, and that is a change in thermal energy. So I'm going to start by drawing that bubble. So I would say this is the iron, right? Its thermal energy is increasing. How do I know its thermal energy is increasing? Because the temperature is increasing, exactly right. What is its initial temperature? Its initial temperature is equal to 20. What's its final temperature? Now, at this point, you might say 1,650. But that turns out not to be quite right. And why is that? The reason is that when you have a system, when you have a substance, if that substance changes, if that substance is changing its thermal energy and it changes its phase in the middle, you have to think about the changes in thermal energy separate. So we think about the change in thermal energy of the solid iron as one piece and the change in thermal energy of the liquid iron as a second piece. We have to keep them separate. We'll see exactly why here in a second, but we have to keep them separate. And so the first thing that happens is the iron warms up to its melting point. And so the final temperature for now is 1,540 degrees Celsius, the melting point of the iron. So I would draw a pretty terrible circle, and that just disappeared. There we go. So that would be our first step. Right? So that's the first thing that happens. The first thing that happens is the iron warms itself up to its melting point. Okay, what's the second thing that happens? The iron melts. Right now the iron is at its melting point. It's going to melt. It's going to turn from a solid into a liquid. So how do we represent that? Well, it's now a bond energy change. So now we say the iron, its bond energy is increasing. How do we know its bond energy is increasing? Because the solid iron is turning into liquid iron. The solid iron is turning into liquid iron. Now, there's a couple, the way you choose to represent this next part is sort of up to you. I'm going to show you the way that I do it. I'm going to say that at the beginning of our process, the iron is all solid. In other words, it's 0% liquid. And then at the end of the process, it's 100% liquid. There are different ways you can represent this. How you do this is not super important, but the point is it's starting as a solid and turning into a liquid. And it's not just some of the iron that is going from a solid to liquid, it is all of the iron that is going from a solid to liquid. How do we know it's all of the iron that turns from a solid into a liquid? Yeah?
Because the final temperature reaches when the phase changes.
That's exactly right. That is exactly right. Remember something I said last week is that you cannot have a thermal energy change while you have a mixed phase. So you cannot have a solid and a liquid that's the same. If you have if you have a substance that's a solid and it's turning into a liquid, it is not allowed to change its temperature until it is fully liquid. And so we know that our system is going to increase its temperature above the melting point, and that guarantees to us that all of the iron must first be turning into a liquid. Okay, so there's our bond energy. Oops, there's our bond energy bubble. And now we need, I took up way more space than I was planning. Let's just see if this will, there we go. So now we need one more thermal energy bubble. So again, we're going in chronological order. We're thinking about what's going to happen over time. So it's going to start by warming up to its melting point. Then it's going to melt. And then we have liquid iron that's going to warm up to the final temperature of the system, which we're told is 1,650 degrees Celsius. And so now we just have another thermal energy bubble. And the only difference between this thermal energy bubble and the one that came before is that we're now talking about liquid iron. So I'm just going to put in parentheses right here that we're now talking about the liquid. That's an L. Sorry, it's not a particularly great L, but that is an L. It stands for liquid. Its thermal energy is increasing because its temperature is increasing, and its initial temperature is 1,540 degrees Celsius, right? Once it finishes the phase change, it's still at that melting point temperature. And then the final temperature is just the final temperature of the system. It's 1,650 degrees Celsius. And there we go. Those are our three energy bubbles. And remember, we figured them out just by thinking what would happen over time, right? Just starting one place. Yes?
Would you also want us to show energy leaving and entering the system as well?
Good, that's the next step, yes. Good question. No, absolutely. Good question. So this goes back to someone else was asking earlier about, is this an open or closed system? So this is an open system, and the rule we're going to give for whether a system is open or closed is that a system is closed unless you have a good reason to be believe that it's open. So what is our good reason for believing this system is open? Well, the answer is, what is the question asking us to find? It is asking us to determine the amount of heat that is added to the iron during the process. What is heat as far as we're concerned? Heat is energy that's coming into or out of the system. Right? If energy is coming into the system must be open. So this problem is telling us the system is open. We would represent that with a nice little dotted line around the edge. And then we might just say, might just draw a little arrow in and say heat is coming in. And there you go. That is an energy interaction diagram. And the next step would be to write an equation. And remember, what is the nice thing about an energy interaction diagram is if you draw your energy interaction diagram correctly, you can always write an equation very quickly, right? Because there's just one change in energy for each bubble, and those changes in energies added up are equal to the energy that's entering or leaving. So I just go bubble by bubble. I'd start here, and I'd say, okay, so we have a change in thermal energy for the solid iron, so I'm going to mention that's a solid. Then we have a change in bond energy as the iron turns into a liquid. And then we have another change in thermal energy as the liquid iron warms up. And all this is equal to the energy that enters or leaves the system, which in this case is just the heat. In this case is just the heat. So let's say that you were solving this problem, and this is as far as you got. This is a lot of points, right? Because what are you doing in this solution? You are demonstrating to me that you understand all the physics that is going on. You are demonstrating to me that you know what information is important for each kind of energy. You are demonstrating that you know the system is open. You are demonstrating that you can write down a basic equation. All of the physics of this problem is in here. All that we want to do now is calculate this number, this Q. Right? So what we would do is the next step is we just start replacing these with the pieces of we would replace these with with this. I don't know what the word is that I'm looking for. But right down here, I have the equation for change in thermal energy. So what we would do is we would say, okay, mc delta T when it's a solid plus delta M delta H. I'll talk about what delta M means here in a second. Plus delta, mc delta T liquid is equal to Q. Right? In other words, the total amount of energy that enters the system is equal to the change in the thermal energy while it's a solid, plus the change in bond energy when it turns into a liquid, plus the change in thermal energy while it is a liquid. If you add all that up, you get the amount of energy that's going into the system. Now, real quickly, let's talk about this delta M. So why do we call it delta M in the bond energy equation? The reason is that it is not necessary, it is not required that all of your substance changes phase. It is possible in certain problems that only half of your substance changes phase, or only a quarter of your substance changes phase. And in that case, your delta M will just be the amount of your substance that changes phase. But in this case, how much of our substance is changing? All of it. It's all turning from a solid to liquid, so it would be just fine to just drop this delta and just call this M. Because all of your substance is turning from a solid into a liquid. If it wasn't all of the substance, then you'd have to figure out how much it was and plug that number in. But because it's all of our substance, we'll just call it M. It's the same M as the other M's. And now you have an equation, and all the information, everything that you need, all the numbers in the equation, except for one, have been given to you. The mass of the iron has been given to you. The specific heat of solid iron has been given to you on the second page. The change in temperature of the solid iron, you can get it right here. It's 1,520 degrees Celsius. We have the mass. Delta H for solid to liquid iron is on the next page. The specific heat for liquid iron is on the second page, and the change in temperature of the liquid iron you can find because you drew a nice energy interaction diagram. And at that point, it would be a matter of plugging into your calculator and figuring out what the number was, which I'm not going to do here because it's not very interesting. And like I said, if you get here, you're at over 90% of the points. Again, I will release this as this is one of the practice quizzes that I'll be posting later today. And I will post solutions to it on Thursday. But before we go, I'd just like to take a really quick look at the second part of the problem and just think about how we might start solving it. So we're not going to solve the whole thing, but we're just going to start solving it. So let's just read it real quick. It says, after it has been melted, the iron is poured into a mold and immediately put into a bucket containing 0.9 kilograms of liquid water. And I put the little asterisks. This is probably not how casting iron works. Some of you might know more about this than me. I certainly do not know a lot, but we're going to pretend this is how it works. When the system reaches thermal equilibrium, the water is a mixture of liquid and gas. How much steam, water, gas, is present in the system when it reaches thermal equilibrium? Treat the iron and water as a closed system. Ignore the internal energy of the mold. And you may find it useful to draw an energy interaction diagram, but are not required to do so, just as was said in the previous part. So this part is more involved than the previous one. There's more going on here. But let's just take a moment to ask ourselves the same question. What kind of energy do we have? And how much is it changing by? So we're given an initial temperature for the water at 0 degrees Celsius. Are we given a final temperature for the water? So I see some shaking of heads. I see one tentative nod. The answer is yes, but this is an example where the information is kind of hidden. Look at this. When the system reaches thermal equilibrium, the water is a mixture of liquid and gas. And we know that if you have a substance that is in a mixed phase, there's only one temperature that it is allowed to be, and that is its phase change temperature. So if you have water that is a mixture of liquid and gas, the only temperature that it can be is the phase change temperature, the liquid to gas phase change temperature, which is 100 degrees Celsius, which is given in the equations and constants down here, right there. But it's not just the final temperature of the water that is 100 degrees Celsius, it is the final temperature of the entire system, because it says when the system reaches thermal equilibrium, the water is a mixture of liquid and gas. And thermal equilibrium is when everything in your system is the same temperature. And so it turns out that the final temperature of not just our water, but also our iron is 100 degrees Celsius. And so what is the iron doing? Just the exact opposite of what it did in part A. In part A, it started as solid, warmed up and turned into a liquid. Now it's starting as a liquid and is cooling down and turning into a solid. Okay? So that is the problem. I will give you the opportunity to work on this on your own, but those are some hints that I will give you. Like I said, I will post, these practice problems will be up in the next 20, 30 minutes. The solutions will be up on Thursday. Like I said, there is one topic that you should go watch the video for. Videos posted on Canvas. You'll see like week 2 short lecture videos, something like that. It's the first one right there. So click on that. Give it a watch before DL if you can. But it's not the most important topic that we'll cover in this course, so if you just see it in DL, that'll probably be fine. All right, have a good rest of your week, everyone. I'll see you next week for the quiz. Yeah.
Accommodations. Would we be able to use that for like quiz?
Yeah,
settings?
yeah, absolutely, yeah.
Do I just like, because I've never used mine before. I
Yeah,
just
yeah.
applied for them last quarter.
Okay, so did you just, so you might not have gotten it if you just got your accommodation letter. I sent out a message about that. Did you get a message from me about that?
So I haven't even gone onto the SDC portal to like pick which accommodations I
Okay,
want.
I see.
I think for me, I don't need to be in a separate room or anything. Sometimes my anxiety causes me to have like panic attacks.
I see.
So I just need like a little bit more time because I'll like be panicking for like a second.
Okay. So yeah, usually what we do is we let the SDC handle the proctoring in that case. just so that you don't have to deal with needing more time when I'm trying to like collect quizzes and that's annoying and all that stuff. So if I have a letter from the SDC for you, you should get an email from me about it. If you're worried that you might not get that you might.
Sometimes you'll start it on the SDC side. I should request which accommodations
Okay.
I want, and then they're gonna send you a letter, and then
Okay.
I think you'll send me an email,
Yep,
right? Okay.
sounds good. Hi.
I have a question
Yeah.
about the kinetic energies,
Uh-huh.
like the formula.
Yeah.
I know the velocity is squared.
Mhm.
Does the squared affect the units for velocity? So you said it's
It does. So yeah, so the units of velocity is meters per second. You square that, you get meters squared per second squared.
okay.
You multiply that by a kilogram and you get a joule.
Okay.
So that's why it's squared, and part of the reason why it's squared, yeah.
Okay, I always got confused. With
Yeah,
that.
yeah.
Thank you.
Yeah. Yeah.
Yeah, I have a question about last question.
Uh-huh.
Yeah, because we read the equation about this, about the delta EB.
Yeah.
Yeah, and I thought that the delta EB have the positive or negative
Mhm.
part.
Yeah.
So does this affect does this have some effects of the negative and positive?
Yeah.
So because I saw the equation about this one,
Mhm.
it has a negative and a positive.
Yeah.
Yeah, and so how can we use
Yeah. So the rule is, if you have a solid turning into a liquid or a liquid turning into a gas, it's a positive change in bond energy.
oh,
And if you have a gas turning into a liquid or a liquid turning into a solid, it's a negative change in bond energy.
oh,
So this was a solid turning into a liquid, so it's positive.
oh,
Yeah. Yeah. Hi.
Just a quick question.
Yeah.
The problem with
Uh-huh.
it, how did you know that it was a
So for part A, the reason was that the question was what we were being asked to solve, to find. It said how much heat goes into the iron during the process. That was the question we were being asked. And heat is always coming into the system. That means that then the system is open. Right? In order for heat to come into our system, the system must be open. And so when I ask us why is, or how much heat is entering the system, that's a good sign that the system is open.
Okay, thank you.
Yeah. I'll be right up.